Great, so now we're going to do the last or the second limit where we have a short correlation time. So that means that tau c is much less than the time that we're looking. So now we're looking out here somewhere after the correlation is, maybe I didn't draw it very well, decayed faster. Okay, so what we're going to do is we're going to put this into our g function again. So we have g is delta squared tau c squared. Now we have our exponential again, minus t over tau c. Remember the last time we did this, we expanded it out. All right, but this time what we're going to do is something a little bit different, right? Here what we're going to do is recognize that if tau c decays, so we're looking way after the tau c. That means when the exponential should be really, really small. The whole term should be small. So what we're going to do is, of course, we're just going to neglect this. Okay, so we neglect that. One thing we know is that if tau c is very small, then t over tau c is very much bigger than 1. This term here is much bigger than 1, so we can neglect the 1 at the end. So that gives us then delta squared tau c squared times t over tau c. All right, so which gives us then delta squared tau c times t. All right, so what we know is that this whole thing is going up into an exponential. This whole thing has to be unitless. Right, so we know automatically that this piece here has units of inverse time. So let's call it gamma, and we'll call that 1 over t2. And we could call it whatever you want, but this is just to make contact with other theories and conventional, notation that people use. Okay? So for now, of course, it makes no difference, but for the language that we want, this is what we're going to do. So that means that this whole thing, g of t, reduces to gamma t, or t over t2. All right, so the f function is then e to the minus t over t2. Okay, so we put that into our line shape. Remember this Fourier transform of the dipole moment correlation function. We have the piece out front, that's the exponential with the average frequency in it. So we have I omega minus omega, the average. And then we have e to the minus t over tau over t2. All right, and so it turns out that the spectroscopy is proportional to the real part of this. So the real part of sigma of omega is proportional to 1 over omega minus omega squared minus 1 over t2 squared. Okay, so this looks like something like 1 over like x squared minus some constant. Right? And this looks like a Lorentzian. All right, so this is telling us that if you look at the line shape and you see it looks Lorentzian, sometimes it's tempting to associate with that what we call homogeneous broadening. right? And the idea basically there is we don't have different molecules. We have every single molecule acts about the same. The correlation time of the frequency fluctuations is very fast. So fast FFCF decay. Right? And the problem is, you go in the lab and you measure some absorption spectra. Sometimes you can kind of say, yeah, that looks more Gaussian, that looks more Lorentzian. But what if you have a couple of peaks lined up next to each other? That's not so easy, right? They all overlap. The main thing that makes a Lorentzian different is this part over here anyway. That's the thing that, from an experimental point, that you can actually see. If you have a single Lorentzian, sure, you could probably tell. But if there's multiple ones, it's not that easy at all to tell what's going on. Okay, and so that's number one. Number two, notice it's a limit. This is a limit. So tau c much less than t is this one. Tau c much greater than t. Inhomogeneous limit. And we already talked about in the discussion what happens when you have two states, right? And you have two states that can interconvert. If they have different frequencies, they switch back and forth. If that switching back and forth is very slow, you see two peaks corresponding to the two frequencies for the species A and B. And as they switch back and forth more quickly, right, then we get this coalescence of the peak in the middle when the exchange is very fast. That is also captured in these limits here. Right, this would be like the slow exchange limit. This would be like the fast exchange limit. But there's no reason why you can't have a physical system that's somewhere in between these two. Well, if you're somewhere in between, then what do you do? Well, then it turns out your line shape is going to be like a convolution of a Lorentzian and a Gaussian. It could be more complicated than that, but people certainly have used that model. So by using a so-called Voigt line shape, you can account for effects of homogeneous and inhomogeneous broadening. But again, it's just curve fitting and making a model. Now, in some cases, it works really well. In NMR, it works great, primarily because the interaction with the environment in NMR is very, very weak. But in almost every other spectroscopy that we use, UV, visible, infrared, it's not the case. The interaction with the environment is very strong. And in chemistry, we're very rarely in only one of these two limits, except for some of the contrived examples that I showed you before. But even the OH stretch has this sort of slow, relatively slow fluctuations due to the rearrangements of hydrogen bonding networks, which is sort of a picosecond timescale. But then a molecule that's hydrogen bonded is going to sort of wobble around very quickly in a cone, and then that can cause a homogeneous contribution as well. So the question is there a measurement that you can do that lets you sort all this out? Is there a measurement that gives you directly this? Can we measure this? The answer is yes. Notice that the prominence of this term relied on our assumption that the statistics were Gaussian. So that's already kind of important. But if you use two-dimensional spectroscopy, you can measure with not too many constraining sort of legalistic qualifications. You can measure this frequency correlation function directly in your experiment. You have to make some measurements, a little bit of analysis to your data, and then you can directly access this frequency fluctuation correlation function, which of course you could then turn around and use to compute the line shape function if you wanted to. Make sure it's consistent. That's a good thing to try to do. But more importantly is you can make a model for this the way we've been doing, and you can pull out, oh, okay, so I think the frequency correlation function should have, a fast term that captures the homogeneous dephasing, and then a slower decaying term that tells me about the inhomogeneous broadening. But the nice thing is it doesn't have to be constant, it can decay. So what does that mean? What does it mean for the frequency fluctuation correlation function decay, it means I imagine I have this line shape like this. And remember, what slow means is that we have some time scale of the measurement, which we could say is this amount of time. And then our frequency fluctuations are like slow. So it looks like there's different species. There's a species here, a species here, a species here. So it looks like it's inhomogeneous. But of course, the system is constantly fluctuating. So the way to think about it is you have a band, a subband, that corresponds to one particular conformation. For example, one hydrogen bond length. Right, which might cause you to have that frequency right there. And there's going to be another molecule, of course, over here, which is going to have a higher frequency. Well, what does higher frequency mean? The higher frequency means the bond length is longer. As I explained, that the OH stretch strongly correlates with the bond length, or the distance between the heavy atoms. So you have a kind of mapping of frequency to structure, which is awesome. Right? But you also know the molecules are interconverting all the time, between this state or between some other state. All right? So what you want to do is you want to say, is there a way that I could tag these molecules and find out how long they turn into these? Seems reasonable, right? So one way to do it is to simply take a pulse or a laser field that's tuned to this frequency here, and whose spectral width is not too broad. I don't excite all the molecules. I'm just going to I'm going to burn out essentially just a few of them that are in this configuration. Then I'm going to do is I'm going to bring another laser field in. Let's make this really simple. It's another laser field that's tuned over here. All right, so I have omega short and omega long. So I'm going to excite the molecules with my omega short field that selects the molecules that are in the correct configuration to absorb there. And then I'm going to see how long does it take them to get long. Well, that's pretty cool, because if I could do that, then I could figure out how long it takes basically to break or stretch a hydrogen bond. So the question is, can I do that? The answer is you can. You can use ultra-short laser pulses in the infrared, tune them to be in this spectral region, tune another one to be in this spectral region, and you excite here, and you probe here, and you look for difference. So we call that transient absorption. Now you might be thinking, well, why only this frequency? Why don't I excite here, and then here, and here, and here? And instead of only looking at where it shows up over here, why don't I see how it shows up at all the other frequencies? So you can do that. And that is essentially what we do when we do two-dimensional spectroscopy. We excite all the different frequencies and we correlate them with all the possible detection frequencies. And depending on whether there is inhomogeneous broadening or not, if there is slow fluctuation, slow enough that on the time scale of us exciting and detecting they don't really change all that much, then we'll see in the two-dimensional spectrum a characteristic shape of the line, the two-dimensional line shape, that will be tilted. And I'll show you examples of this in the last couple lecture segments. All right, so the point is, this Kubo line shape theory is very powerful. It lets you think conceptually about dynamics, timescales of frequency correlations, and how that influences the spectral broadening that you see in the lab. The frequency, we know, largely comes from the energy gaps in the molecules, which you could do without any of this. But there's counterexamples, right? Our chemical exchange case. If it's fast, you're going to see the average. There's no molecule in there that has this frequency. But the spectroscopy lies to you. The spectroscopy is lying. It's saying, yeah, there's molecules, they all have that frequency, which is, of course, ludicrous. So then you might ask yourself, is there a way that I can do chemical exchange in the same way that I could do spectroscopy of this line shape? And the answer is you can. And I'll show you examples of that too, where you can use two-dimensional spectroscopy to track chemical reactions even when they're fast. All right, so obviously there's too many spectroscopy methods to list them all. All the methods are described by the response functions that we derived. you pick the right one or the appropriate one for the kind of spectroscopy that you're interested in, you'll notice there's certain correlation functions. For the linear one, it's a dipole moment correlation function. For 2D IR or 2D electronic spectroscopy, it'll be 3 dipole moments. And that correlation, there's going to be many different combinations. They all give rise to different pathways in your signal, and you can identify them, where they show up in the spectrum, from how they what their trace is through Liouville space. And that's something I will also show you in the last basically 2 or 3 lecture segments. Okay, but as far as things go that are, I consider sort of like absolutely mandatory to understand as best as you can, the first is why we have relaxation, because of coupling to a bath. The theory that we use treats that coupling as being weak. That allows us to use second order perturbation theory, and we derive Redfield theory. The second thing is, how can I understand spectral line shapes in an intuitive way? Meaning, if I just had some gut feeling about what my solvent or my environment was doing to the molecule I was studying, how would I be able to guess or understand what the nature of that dynamics was by looking either at the spectrum or, faced with the conundrum, designing new experiments that let me get more information that you can get than you could deduce directly from the spectrum here. Okay? So I think this is very nice. This is called the Kubo theory, by the way. It's from the 1960s, so it's relatively new, I guess, in some sense. And the hardest part, I think, in the derivation is the cumulant stuff. So I made a separate little, I don't know, it just goes through a bunch more lines about it so that you can see maybe how those steps go. Maybe not. I don't know. It's tricky. It's tricky for me too. Most of the notes that you find on it, they gloss over those steps and they don't really explain them very clearly. I'm not sure exactly why that is. I always assumed it's because it's really obvious, and then I try to do it and it's like I see nothing obvious about it. But I'm not the math genius, so that probably explains that. All right, so we'll stop there.